All right, thanks very much everyone for giving me this opportunity. Today I would like to dedicate my talk to the studies that we conducted with Frank exclusively since 2004. Our vision was to develop something simple that allows practitioners to use modified computational field theory as well as distributed field theory when they analyze large buildings, because as we have seen so far, continuum models are really limited to a part of a structure, a small segment, but what are you going to be doing if you have a 10-story building, 20-story building? Can you do a nonlinear finite element analysis? So that was the objective we started. That requires a software capability, not just for analysis, but also for result visualization. So that is my objective in this presentation. This is my first semester, 2004, mechanics of reinforced concrete, which I took from Frank, and that's the beginning of my journey and these studies. So 21 years since then. So we all came to the performance-based assessment, which requires multiple analysis. The issue is not just doing one analysis, which is time-consuming enough, but you have to do 20, 30 analyses. So you need something fast, you need something computationally efficient, but the tools that we have has issues with capturing the shear response, especially important for older structures. So that's the focus, something fast, large structures capture shear response. So for that objective, what we have worked on, my PhD was to develop Vector 5 coding. After my PhD, we continued developing Formworks Plus with Raymond, as well as Janice with various summer students. So I'm going to summarize these studies. So what we have done in the past 21 years is to consider static load conditions, which could be monotonic, cyclic, arbitrary, if you have a arbitrary loading. We also did dynamic implementation, so you can do time history, earthquake, blast, and impact load analysis using the tools that we developed. In terms of element types, slender elements are something which I did in my PhD studies. And then with Professor Mikhailov, I'm fortunate to see he's in the room, we implemented the deep beam element based on his 3PK. So you can have a frame, some of the beams are deep, some of them slender, so that was a permistat. We also did beam column joints, which is really important. It's a main failure location for older structures in particular. So this is what I did in my PhD. It's a layered element based on distributed field theory. This is for only slender elements, considering shear, flexural, and axial force interaction. This is what we did with Dr. Mikhailov. It's a really powerful model. We implemented it fully, and I'm going to show some results soon. That's the other type of element. We also did beam column joints. This comes from University of Washington. We adopted that model. It's a two-dimensional continuum model, but there's interface. You can attach your slender beam column elements to this one. So 13 degree of freedom element that we considered won't slip, as well as shear strut captured by this element. Solution algorithm, we published on this one. I'm not going to be going deep into it, but it's essentially K times U equal to P, but it's a dynamic solution. Over the years, 148, so that's the number we modeled, analyzed, validated with 148 specimens. So I'm going to just sample what we have done. Monotonic loading, these are the specimens that we modeled coming from various researchers, international, some Asia, some Europe, some United States, Canada. I got involved with this one during my PhD studies as well, University of Toronto. The model that we are using, as I said, it has to be simple. It's a stick model, but in terms of graphical visualizations, we came up with an approach. We explode the elements, show layers, and show smeared cracks. So that makes it sort of look like it's a continuum model. It is not, but you still see the critical information. You can see the crack widths, right? It's not going to be perfect. You are not going to be getting a single discrete crack, but in terms of simulated cracking, you are still going to get the failure at the right location. You can see the crack widths. You can see reinforcement stresses, which I'm going to show it later. So if it's green, it's yielding, etc. So sort of, this is like making it a two-dimensional tool. It looks like a two-dimensional tool. And compare it with other macro models. If you used something else, this is what you would get if you don't have this two-dimensional explosion. So we found a big benefit of improving the visual capability, so that's something we spent good time. You can see the pushover responses experiment. The blue one in this presentation will always be the tool that we developed, Vector 5. So that's just one example. You can really get really incorrect responses if you are using just some general purpose tools, especially for shear critical structures. Very overly conservative results that we got for this frame. Cyclic loading, these are shear walls. Again, I'm showing the exploded views. The model is a stick model, but if you explode, you see bar stresses, you see stress contours. I think there are some descriptions here. So you can see the cross-section view with stresses. You can see the hysteresis response comparison. So that's another application. Deep beam modeling with Dr. Mikhailov, we looked at 18 large-scale tests conducted. You can see very simple model. You can do this in a minute. And also, all the options are preset. You are not supposed to select or change the models. So everything is done with one set of parameters, because this is intended for practitioners. You shouldn't be tweaking or trying different options. So you can see deep beams. This is the crack pattern. Again, nothing perfect, but at least you get inclined shear cracking. Responses are comparable to a sophisticated 2D high fidelity FEM. So this is what we got from Vector 5. Of course, there are issues with ductility. It's not exactly the same, but that is a challenge in general. This is another one, as you can see, pretty comparable, even better in some aspects than two-dimensional high fidelity finite element. We have a paper on this one, so I'm not going to go too much into this. Beam column joints, you can see with no joint modeling, if you model joints, this is what you are going to be getting: bone slip, joint shear cracking. That's another option. So you would model your joints using this element. This is sort of summary table for all static load specimens, and you can see the numbers. Average is pretty good. Coefficient of variation 11.4% for everything that we have done. Dynamic loads, 62 specimens we did, coming from all those researchers. So for the sake of time, and also you can get the moment shear diagrams. Practitioners really like it, because in a continuum model, what you get is stress contours. Some practitioners have trouble using it for design purposes. So you can see this is the maximum moment, this is the maximum shear. You can see this is the dynamic response time, history, displacement, peak, reaction. Blast tests, blue one is Vector 5, green one comes from LS Dyna. LS Dyna has two concrete models. One is WCM, I think, concrete damage model, I think, which is the solid one. Sorry, I realize the legend is cut. The other one is Winfrin model. So depending on which model you choose in LS Dyna, you might get radically different responses. This is better. LS Dyna analysis is not something we did. It comes from the people who did experimental testing. So they use LS Dyna, and this is coming from the thesis of the PhD student who did this study. You can see Vector 5 simulations are reasonably well corresponding. A large frame, two columns, shear critical, so we modeled this one. You can see, hopefully this should work. Maybe I should click. This is like a video which shows how Okay, it's working. So this is the time history, and you can see the time. You can see crack widths. It's an earthquake loading. You can see reinforcement stresses for this one. And you see the failed column. This is the failure condition, rebar ruptured or shear failure, whatever it is. You need to zoom in and you can see the conditions of the column. If you use another macro model, this is what you are going to be getting, plastic hinge model. This is from SAP 2000, so we try to give as much results as possible. This is the OpenSeas. My PhD student did it, so he didn't get any visual results from OpenSeas. Seismic load modeling, you need to do development analysis and analyze the results. My student spent a lot of time to see how much time it takes to do all of these. He considered 7 ground motions 6 times. This is what I meant. It's not a single analysis, but you need to go through these analyses, totally 126, more than 620 hours, 11 days of runtime. This is just the software running, even if when you use something super simple like this. So we are talking about significant time still. So he compared different tools. You can see Vector 5, OpenSeas, SAP 2000, especially with general purpose tools. The discrepancy, the variation is huge, as you can see. OpenSeas Vector 5 came really similar to each other in terms of prediction accuracy. These are fragility functions. That's what we want for the probability of collapse for different limit states, immediate occupancy, life safety. So these are all possible, but you need some fast tools. You cannot use a sophisticated tool. It would take months to do these type of analyses. So summary table, this is for dynamic. Almost one mean. Mean do not mean much because some of them might be really high, some of them might be really low, so coefficient of variation is a better representative, which is about 15% reasonable results that we got for all dynamic specimens. So still, modeling shear is challenging. We need fast analysis tools with graphical pre and post processors because you need to do multiple analysis and you need to encourage engineers to run it again, see the issues, fix the models, boundary conditions, response, etc. So Frank Vecchio's analysis algorithms, which forms the basis of Vector 5 and other vector programs, helped greatly advance the nonlinear analysis of concrete structures. His Tempest, which is now Vector 5, was further developed in the last 2 decades as Vector 5 for these load conditions. So that's pretty much the summary. 148 simulations, static dynamic, mean is almost 1, 13.4% coefficient of variation, and I call this a good result overall using the same set of analysis parameters, no tweaking involved. So thank you very much. I really thank Frank for giving me this opportunity since 2004 to get involved in this exciting studies. Thanks very much.